Hi everyone, welcome back to ChemHelp ASAP. Today we're going to be talking about kinetics, and specifically we're going to be talking about the integrated rate law for the zero order reaction. Let's get started. Suppose we have a general reaction, A going to B. We can write our differential rate law very generally like so. We're monitoring the decrease in concentration of A. Of course, that simply equals K times the concentration of A to the N. Now, for this video, we are specifically talking about the zero order rate law. So that means our value of n equals 0, which changes how we write the rate law to this, a to the 0. Remembering, of course, that this rate law right here is our differential rate law. To get to our integrated rate law, we simply integrate this expression right here to get a new expression right here. Of course, after we have integrated, this is now our integrated rate law. So at this point, we are relating concentration to time, whereas in our differential rate law, we related rate to concentration. So let's show how we can use this integrated rate law as a linear plot. So rewriting my rate law up here in the upper right, I want to show how this expression fits into the y equals mx plus b form. So let's take a look at all of these different elements and what information we can get from them. Our y value is simply our concentration of A. So let's write that right down here. Our mx term, of course, matches up really nicely with our negative kt, where x equals t, and our slope is going to give us a negative k value. Finally, our b, or our y-intercept, is simply our initial concentration of A, which we will write right down here. So once we have the equation of the line, we get so much information about our rate law. So let's see how this applies to a problem. Here is the reaction that we are monitoring, and here is our data table. Again, we're just getting concentration versus time here. And specifically, we are monitoring one of our reactants here, our N2O, or dinitrogen monoxide, and you can see it is decreasing because, of course, it is a reactant. So here is our plot right here. You can see it is nice and linear. I have time as my x value, as my independent variable, and of course concentration is on the y-axis as my dependent variable. And on the screen, I have my equation of the line. Again, any spreadsheet application will give you this equation of the line unless you really like to calculate this out by hand. So already we have so much information. We have our slope, which remember gives us our negative k value. So our value for k is 0.0002, and our intercept gives us our initial concentration of N2O, which is simply 0.4606. Okay, so now for a problem given all of this data. Let's calculate the time needed for the N2O concentration to reach 0.1 molar. So we know the concentration we want to reach, and we just want to know how much time is it going to take to get there. Well, looking at our data table, you can see we've monitored to 900 seconds and we have not gotten to 0.1 molar. So it's obviously going to take more than 900 seconds, but let's figure out exactly how much more time it's going to take. Because we're relating concentration and time, we want our integrated rate law right here for our zero order reaction. And let's plug in what we know. We know the concentration we want to reach. That's going to be our 0.1 molar, so we're putting that right here. We have our value for K, so let's plug that in right here. Again, we are solving for time. We want to know how much time it's going to take to reach 0.1 molar. And we know our initial concentration of N2O. That was given to us by our intercept, and that is simply, again, our 0.4606. So all we need to do is solve this equation for time. And our time ends up being 1,803 seconds, which might be easier to report in minutes, which would be 30.1 minutes. And again, this makes sense because we went all the way to 900 seconds, and we're definitely not at 0.1 molar. I hope you found this video helpful, and thanks so much for watching.